Hello students, my name is Ankit Darela, Department of Electronics and Communication, BBD University. We are studying the top subject, Microprocessor and Interfacing. We will continue with the logical instructions. CMC. CMC stands for complement the carry flag. It performs complement operation on the carry flag and the result is stored in the carry flag. The result of execution of this instruction can be shown just by executing CMC. Now suppose carry flag had the data 1 before the execution of CMC. So after executing CMC, the data will be 0. Next is STC. STC stands for set the carry flag. It sets the carry flag to the one state immaterial of its earlier value. So if the carry flag is 1, then also it will set to 1, and if it is 0, then also it will set to 1. So ultimately the carry flag will be set to 1 after the execution of this instruction. Next is CMPR. CMP is a mnemonic that stands for compare accumulator, and R stands for registers A, B, C, D, E, H, L or M, where M is the HL pair location. This instruction is used to compare contents of the accumulator with R. The result of compare operation will be stored in the temporary register. Temporary register is an internal register that is not accessible to the programmer. As R can have any of the 8 values, so there are 8 opcodes for this type of instruction. It occupies only 1 byte in memory. For example, CMPE. Now suppose before the execution of this instruction, A has the value F5H, E has the value 25H, temporary register has the value 45H. So after executing this instruction, the temporary register will have the value D0H and the flag status will be carry flag will be 0, auxiliary carry flag will be 1, 0 flag will be 0, parity flag will be 0 and sign flag will be 0. Next is CPI D8. CPI is a mnemonic that stands for compare immediate with accumulator, and D8 stands for any 8-bit data. This instruction is used to compare accumulator with 8-bit immediate data. The result of the comparison will be stored in an internal register not accessible to the programmer. All the flags are affected based on the result and it occupies 2 bytes in memory. For example, CPI F5H. Now suppose before the execution of this instruction, A has the value 25H, temporary register has the value 45H. So after executing CPI F5H, the result will be 30H, which will be stored in the temporary register. The status of the flags will be carry flag will be 1, auxiliary carry flag will be 1, 0 flag will be 0, parity flag will be 1 and sign flag will be 0. Next is instruction RLC. RLC stands for rotate left accumulator. It rotates the accumulator contents to the left by 1 bit position. In this instruction, the bit that moves out from the MS bit position goes to the vacancy created in the LS bit position. Also, carry flag gets a copy of the bit moved out from the MS bit position. We have to notice that carry flag is not involved in the rotation and it is only 8-bit rotation of accumulator contents. Only carry flag is affected by this instruction execution. This instruction is useful to check the value of the ms bit of accumulator, perform rotate left, and the carry flag will be affected. It is also useful to perform multiplication by 2, rotate the accumulator to the left. It works correctly for unsigned numbers as long as the ms bit of accumulator is a 0 before a rotation. For example, accumulator has the value 24H and carry flag has the value 1. So after executing RLC, the result will be 48H which will be stored in the accumulator, and the value of carry flag will be 1. Next is RAL. RAL stands for rotate accumulator left involving carry flag in rotation. It rotates the accumulator contents to the left by 1 bit position. After rotate left operation, the bit moves out from the ms bit position and goes to the carry flag. And in this process, it also moves out the earlier carry bit to the vacancy created in the ls bit position. We have to note that the carry flag is involved in the rotation, and it is a 9-bit rotation of accumulator and the carry flag contents. Only carry flag is affected by this instruction execution. This instruction is useful to check the value of ms bit of accumulator, perform rotate left, and the carry flag value is changed. It is also used to perform multiplication by 2. It works correctly for unsigned numbers as long as the ms bit of accumulator and the carry flag are 0 before rotation. It is also used to introduce a new bit value to the ls bit position. Put this bit value in the carry flag and then execute this instruction. For example, before the execution of this instruction, accumulator has the value 24H and carry flag has the value 0. So after executing RAL, accumulator will have the value 48H and carry flag will have the value 0. Next is RRC. RRC stands for rotate right accumulator. It rotates the accumulator contents to the right by 1 bit position. After rotate right operation, the bit moves out from the ls bit position and goes to the vacancy created in the ms bit position. Also, the carry flag gets a copy of the bit moved out from the ls bit position. We have to note that the carry flag is not involved in the rotation, and it is only 8-bit rotation of accumulator contents. Only carry flag is affected by this instruction execution. This instruction is useful to check the value of ls bit of accumulator and perform a rotate right. It is also used to perform division by 2. It works correctly for unsigned numbers as long as the ls bit of accumulator is a 0 before a rotation. For example, suppose accumulator has the value 48H and carry flag has the value 1 before the execution of this instruction. Then after executing RRC, the result will be 24H, which will be stored in the accumulator, and the value of carry flag will be 0. Next is RAR. RAR stands for rotate accumulator right involving carry flag in rotation. It rotates the accumulator contents to the right by 1 bit position. As can be seen, after a rotate right operation, the bit moves out from the ls bit position and goes to the carry flag, and in the process moves out the earlier carry bit to the vacancy created in the ms bit position. We have to note that the carry flag is involved in the rotation, and it is a 9-bit rotation of accumulator and the carry flag. and only carry flag is affected in the execution of this instruction. This instruction is useful to check the value of LS bit of accumulator and perform rotate right operation. It is also useful to perform division by 2. It works correctly for unsigned numbers as long as the LS bit of accumulator and the carry flag are 0 before rotation. It is also used to introduce a new bit value to the MS bit position and put this bit value in the carry flag and then execute this instruction. For example, the accumulator had the value 48H and carry flag had the value 0 before executing this instruction. So after executing RAR, the result 24H will be stored in the accumulator and the carry flag will have the value 0. So this is how RLC and RAL can be demonstrated, and the compare operations can be performed using this CMP operation. Next, we will study the branching instruction. The branching instruction consists of unconditional jump instructions, JMP A16, which is unconditional direct jump, PCHL, which is unconditional indirect jump, JNC A16, jump if not carry, JC, jump if carry, JNZ, jump if not 0 result, JZ A16, jump if 0 result, JPO A16, jump if parity odd, JPE A16, jump if parity even, JP A16, jump if positive, JM A16, jump if minus. So we will start with the unconditional jump instructions. In simple programs, there is a linear program flow from the first instruction to the last instruction in the program. But the real power of a computer exists in its ability to change program flow, and the program should be written to take advantage of this ability. Change in program flow is needed when a sequence of instructions is to be executed repeatedly. It is also needed when it is required to choose between two or more sequences of actions based on some conditions. The branch group of instructions in 8085 affects such a change in the program flow. The branch instructions can be used for affecting a forward branch or a backward branch. JMP A16. JMP is a mnemonic that stands for jump, and A16 stands for any 16-bit address. This instruction is used to jump to the address A16 provided in the instruction. For example, JMP F950H. In this example, after executing JMP F950H, the results are loaded in the PC with the value F950H, overwriting the earlier value of F823H. Hence, after execution of JMP F950H, the instructions at the location F950H will be fetched and executed. Next is PCHL. PCHL is a mnemonic which stands for load PC with the contents of HL. PC means program counter. This instruction is used to jump to the address provided in HL register pair. Thus, it is unconditional indirect jump instruction. Because of its indirect jump feature, it is not very commonly used. It is a 1-byte instruction compared with the direct jump instruction, which is a 3 bytes long. Because of this size advantage, it can be useful for jumping to a frequently used portion of the program. For example, before the execution of this instruction, HL had the value F950H and PC had the value F823H. So after executing PCHL, the result will be F950H, which will be stored in PC. Next is conditional jump instructions. First one is JNC A16. JNC is a mnemonic which stands for jump if not carry, and A16 stands for any 16-bit address. This instruction is used to jump to the address A16 provided in the instruction only if carry flag value is 0. If carry flag value is 1, program flow continues sequentially. For example, JNC F950H. It is a 3-byte instruction. After 8085 fetches JNC F950H, the PC value would have been automatically incremented by 3 to F823H. But JNC F950H instruction execution results in loading of PC with the value F950H only if carry flag value is 0. Hence, after execution of JNC F950H, the instruction at memory location F950H will be fetched and executed only if carry flag value is 0. Next is JC A16. JC is a mnemonic which stands for jump if carry. This instruction is used to jump to the address A16 provided in the instruction only if carry flag value is 1. If carry flag value is 0, program flow continues sequentially. Next is JNZ A16, jump if not 0 result. JNZ is a mnemonic which stands for jump if not 0 result. This instruction is used to jump to the address A16 provided in the instruction only if result is not 0, indicated by a 0 flag value of 0. If 0 flag value is 1, program flow continues sequentially. Next is JZ-A16. JZ is a mnemonic which stands for jump if 0 result. This instruction is used to jump to the address A16 provided in the instruction only if result is 0, indicated by 0 flag value of 1. If 0 flag value is 0, program flow continues sequentially. Next is JPO A16, jump if parity odd. JPO is a mnemonic which stands for jump if parity odd. This instruction is used to jump to the address A16 provided in the instruction only if parity flag is 0. If parity flag value is 1, program flow continues sequentially. Next is JPE A16. JPE is a mnemonic which stands for jump if parity even. This instruction is used to jump to the address A16 provided in the instruction only if parity flag value is 1. If parity flag value is 0, program flow continues sequentially. Next is JP-A16. JP is a mnemonic which stands for jump if positive. This instruction is used to jump to the address A16 provided in the instruction only if sign flag value is 0. If sign flag value is 1, the program flow continues sequentially. And the last one is JM A16. JM is a mnemonic which stands for jump if minus. This instruction is used to jump to the address A16 provided in the instruction only if sign flag value is 1. If sign flag value is 0, program flow continues sequentially. We'll continue with the branching instruction where call instructions have come up. The difference between a jump instruction and a call instruction can be explained If a jump instruction is executed, we jump to the destination location and the execution carries on from there without bothering to come back later to the instruction after the JMP. If a call instruction is executed, we jump to the subroutine and the execution carries on from there till the RET or a return instruction is executed in the subroutine. And then we come back to the instruction after the call in the main program. The address of the next instruction after the call instruction is called the return address. This is the address to which the program flow returns when the RET instruction is executed by the 8085. By the time the 8085 fetches the call instruction, the PC would have been incremented by 3 and will be pointing to the next instruction after call. In other words, PC will have the return address by the time the call instruction is fetched. In order to facilitate such a return, the call instruction will first of all store above the top of stack the return address. Only then the branch to the subroutine takes place. So this is the difference between the jump and the call instruction. We'll start with the conditional call instruction. The conditional call instructions of 8085 branch to a subroutine based on the value of a single flag. The branch takes place based on the value of carry flag, zero flag, parity flag, or sign flag. There is no call instruction based on the value of auxiliary carry flag. So first is CNC A16. CNC is a mnemonic which stands for call if not carry. This instruction is used to branch to the subroutine whose 16-bit address is provided in the instruction only if carry flag value is 0. If carry flag value is 1, the program flow continues in the main program sequentially. Next is CCA16. CC is a mnemonic which stands for call if carry. This instruction is used to branch to the subroutine whose 16-bit address is provided in the instruction only if carry flag value is 1. If carry flag value is 0, program flow continues in the main program sequentially. Next is CNZ A16. CNZ is a mnemonic which stands for call if not 0 result. This instruction is used to branch to the subroutine whose 16-bit address is provided in the instruction only if a result is not 0, indicated by 0 flag value of 0. If 0 flag value is 1, program flow continues in the main program sequentially. Next is CZA16. CZ is a mnemonic which stands for call if 0 result. This instruction is used to branch to the subroutine whose 16-bit address is provided in the instruction only if a result is 0, indicated by 0 flag value of 1. If 0 flag value is 0, program flow continues to the main program sequentially. Next is CPO A16. CPO is a mnemonic which stands for call if parity odd. This instruction is used to branch to the subroutine whose 16-bit address is provided in the instruction only if parity flag value is 0. If parity flag value is 1, program flow continues in the main program sequentially. Next is CPE A16. CPE is a mnemonic which stands for call if parity even. This instruction is used to branch to the subroutine whose 16-bit address is provided in the instruction only if parity flag value is 1. If parity flag value is 0, program flow continues in the main program sequentially. Next is CPA16. CP is a mnemonic which stands for call if positive. This instruction is used to branch to the subroutine whose 16-bit address is provided in the instruction only if sign flag value is 0. If the sign flag value is 1, program flow continues in the main program sequentially. And the last one is CMA16. CM is a mnemonic which stands for call if minus. This instruction is used to branch to the subroutine whose 16-bit address is provided in the instruction only if sign flag value is 1. If the sign flag value is 0, program flow continues in the main program sequentially. Next is the conditional return instruction. The conditional return instructions of 8085 affect a return to the main program based on the value of a single flag. The return takes place based on the value of carry flag, zero flag, parity flag, or sign flag. There is no return instruction based on the value of auxiliary carry flag. So the first one is RNC-A16. RNC is a mnemonic which stands for return if not carry. This instruction is used to return to the main program only if carry flag value is 0. If carry flag value is 1, program flow continues in the subroutine sequentially. It is a 1-byte instruction. Next is RC-A16. RC is a mnemonic which stands for return if carry. This instruction is used to return to the main program only if carry flag value is 1. If carry flag value is 0, program flow continues in the subroutine sequentially. Next is RNZ-A16. RNZ is a mnemonic which stands for return if not 0 result. This instruction is used to return to the main program only if result is not 0 indicated by 0 flag value of 0. If 0 flag value is 1, program flow continues in the subroutine sequentially. Next is RZ-A16. RZ is a mnemonic which stands for return if 0 result. This instruction is used to return to the main program only if result is 0 indicated by 0 flag value of 1. If 0 flag value is 0, program flow continues in the subroutine sequentially. Next is RPO-A16. RPO is a mnemonic which stands for return if parity is odd. This instruction is used to return to the main program only if parity flag value is 0. If parity flag value is 1, program flow continues in the subroutine sequentially. Next is RPE-A16. RPE is a mnemonic which stands for return if parity is even. This instruction is used to return to the main program only if parity flag value is 1. If parity flag value is 0, the program flow continues in the subroutine sequentially. Next is RP-A16. RP is a mnemonic which stands for return if positive. This instruction is used to return to the main program only if sign flag value is 0. If sign flag value is 1, program flow continues in the subroutine sequentially. Next is RM-A16. RM is a mnemonic which stands for return if minus. This instruction is used to return to the main program only if sign flag value is 1. If sign flag value is 0, program flow continues in the subroutine sequentially. And the last is RSTN. RSTN, here N signifies the number 0 to 7 only. Thus, the 8 possible RST instructions are RST0, RST1, RST2, RST3, RST4, RST5, RST6, and RST7. These all are basically single byte call instructions. For example, RST2 is functionally equivalent to call 2 into 8, which is call 0010H. The advantage of RST2 is that it is only 1 byte, whereas call 0010H is a 3 byte long instruction. Thus, RST instructions are useful for branching to frequently used subroutines. So these are the branch operations: unconditional branch and conditional branch. We have studied JMP call, JMP address jump to the address specified, go to call address jump to the address specified but treat it as a subroutine, and RET return from a subroutine. The addresses supplied to all branch operations must be 16 bits. These are the conditional branch instructions we have studied: JZ, JNZ, JC, JNC, JP, and JM. And now we will study the NOP and stack instructions. Stack is a LIFO, last in first out, data structure implemented in the RAM area and is used to store addresses and data when the microprocessor branches to a subroutine. In the programmer's view of 8085, only the general purpose registers A, P, C, D, E, H, and L and the flag registers have been told so far, but in the complete programmer's view of 8085, there are two more special purpose registers, each of 16-bit width. These are stack pointer SP and the program counter PC. Let us say SP contents are FC78H and we want to read information from a stack location. In this case, we are not interested in reading from a location whose address is less than the memory address present in SP. This is because 8085 interprets them as useless information. So we can load the register pair BC when SP contents was FC78H. We can study these stack instructions by the instructions written over here. First is pop RP. This instruction loads a register pair RP by popping out 2 bytes from the top of the stack. RP is the register pair BC, DE, or HL. This pair is generally called PSW, which consists of accumulator and flag, and this PSW is called processor status word. In the PSW, accumulator is the MS byte and the flag register is the LS byte. 2 bits are used in an opcode to specify a register pair. Thus, actually, 4 register pairs can be specified using 2-bit code for RP. In all, there are 5 register pairs. For example, we have the instruction pop. We have the instruction pop B. So before executing this instruction, SP had the value FE06H, FE06H had the value 66H, FE07 had the value 55H, accumulator had the value 33H, and flags had the value 44H. So after executing this instruction, SP becomes FE08H, accumulator becomes 55H, and flags become 66H. Next is push RP. This instruction stores contents of register pair RP by pushing it into 2 locations above the top of the stack. RP stands for BC, DE, HL, or PSW. As RP can have any of the 4 values, there are 4 opcodes for this type of instruction. It occupies only 1 byte in memory. For example, push B. So before executing this instruction, B had the value 77H, C had the value 88H, SP had the value FB06H, FB05 had the value 66H, FB04 had the value 55H. So after executing push B, SP becomes FB04H, FB05 has the value 77H, and FB04 has the value 88H. Next is SPHL. This instruction loads the stack pointer with the contents of register pair HL. It is an indirect way of loading the stack pointer, and as such it is not quite commonly used. It occupies only 1 byte in memory compared to LXI SP instruction, which is 3 bytes long. Because of this advantage, SPHL can be useful when SP is required to be initialized to a specific value a number of times in a program. Now suppose HL had the value FB50H and SP had the value F900H. So after executing SPHL, SP becomes FB50H. Next is LXI SP D16. LXI SP D16 instruction is a special case of LXI RP D16. LXI SP instruction is used to load 16-bit immediate data to the SP. It occupies 3 bytes in memory. For example, LXI SP FC06H. So by executing this instruction, the value of SP becomes FC06H. Next is XTHL. XTHL is a mnemonic which stands for exchange top of stack with HL. This instruction exchanges the contents of the top 2 locations of the stack with the contents of register pair HL. It is not the exchange of SP with HL. It occupies only 1 byte in memory. The result of the execution of this instruction can be shown like suppose SP had the value F900H, HL had the value FB50H, F900H had the value 25H, F901H had the value 35H. Then after executing XTHL, HL becomes 3525H, F900H becomes 50H, and F901H has the value now FBH. Next is INX SP. INX SP instruction is a special case of INX RP. INX SP instruction is used to increment the SP contents by 1. It occupies only 1 byte in memory. Now suppose SP had the value FC00H, then after executing INX SP, SP becomes FC01H. Similarly, there is DCX SP. This is also a special case of DCX RP, which is used to decrement the SP contents by 1. Suppose SP had the value FC00H, so after executing DCX SP, the SP becomes FBFFH. Next is DAD SP. DAD SP instruction is a special case of DAD RP. DAD SP instruction is used to add SP contents to HL contents and store the result in HL register pair. It occupies only 1 byte in memory. For example, HL had the value 0234H and SP had the value F850H. So after executing DAD SP, HL becomes FA84H and only carry flag is changed, which becomes 0. No other flags are changed in this instruction. Next is NOP. NOP is an instruction that cannot be classified under any group of the instructions, NOP is a mnemonic that stands for no operation. This instruction does not do anything. Still, it is quite useful. It occupies only 1 byte in memory. It has the opcode 00H. NOP instruction is very useful for generating small time delays of the order of a few microseconds. NOP instruction is useful when we require to delete a few instructions in our program. It is useful when we require to insert a few instructions in our program. Next is HLT. HLT means halt. It is used to halt our program. So these are also called the machine control instructions. Halt, as I told, can be used for stop executing the program. NOP is for a no operation, exactly as it says, do nothing. Usually used for delay or to replace instructions during debugging. So this is the stack area. Stack is an area of memory identified by the programmer for temporary storage of information. The stack is a LIFO structure, last in, first out. The stack normally grows backwards into memory. In other words, the programmer defines the bottom of the stack and the stack grows up into reducing address range. Given that the stack grows backwards into memory, it is customary to place the bottom of the stack at the end of memory to keep it as far away from the user programs as possible. In the 8085, the stack is defined by setting the SP stack pointer register LXI SP FFFFH. This sets the stack pointer to location FFFFH end of memory for the 8085. Saving the information on the stack. Information is saved on the stack by pushing it on. It is retrieved from the stack by popping it off. The 8085 provides two instructions, push and pop, for storing information on the stack and retrieving it back. Both push and pop work with register pairs only. Push B, decrement SP, copy the contents of register B to the memory location pointed to by SP. Decrement SP, copy the contents of register C to the memory location pointed to by the SP. Similarly, there is pop D. Operation of the stack. During pushing, the stack operates in a decrement then store style. The stack pointer is decremented first, then the information is placed on the stack. During popping, the stack operates in a use then increment style. The information is retrieved from the top of the stack and then the pointer is incremented. The SP pointer always points to the top of the stack. LIFO. LIFO means last in, first out. The order of push and pop must be opposite of each other in order to retrieve information back into its original location. So in the next class, we will study the interrupts and its priorities and how the interrupts of 8085 are there.